Let's say that you have a conductor of a circular cross-section area. The cross-section area is A, and the length of the conductor is L. And suppose that the conductor is made of a material of resistivity ρ. The resistance of this section of the conductor is given by R equals ρ L over A. In this experiment, we'll study the resistance versus length in part 1, and we will end up plotting the resistance on the y-axis versus the length on the x-axis. So, in a case like this, let's rewrite our equation as R equals ρ over A multiplied by L. Notice that in part 1 we will keep the cross-section area constant and we will be changing the length. So the quantity between parentheses is constant because the cross-section area is constant and the resistivity is constant since we are using the same material. So by comparing this equation with the graph, we have the resistance on the y-axis, we have the length on the x-axis, and the quantity between parentheses is constant. So we have y equals a constant times x, which is the equation of a straight line that passes through the origin. The slope of the line is the constant of the relation, which is in this case ρ over A. Now in part 2 of the experiment, we will keep the length constant and we will change the cross-section area A. And in part 2, we will end up with a plot of the resistance on the y-axis versus 1 over A, 1 over the cross-section area on the x-axis. So let's rewrite the equation as R equals ρ times L multiplied by 1 over A. Now notice that the resistance is on the y-axis. The whole thing between parentheses 1 over A is on the x-axis. And then ρ and L are both constants in part 2 of the experiment. So once again, we have y equals a constant times x, which is the equation of a straight line that passes through the origin. However, in this case, notice that the slope of this line is the constant of the second relation, which is ρ times L. Let's start with the signal generator and set output 1 to a positive up-ramp wave of a frequency 1 Hertz. And let's leave the voltage, the amplitude at 1 volt and set this to automatic. We have to measure the voltage. So we are using a voltage sensor which is connected to channel A right here. Here is the voltage sensor. And also we will use the built-in sensor to measure the current. So to add this sensor, we click on the output voltage current sensor. And let's keep in mind that this will be used to measure the current. Also, we have to set the recording conditions so that it stops after 1 second. So we'll set the stop conditions to time-based and set this to 1 second. Now, in order to be able to get the reading of the sensors, notice in this part we are interested in having the voltage versus current so that we can get the resistance. So I'm going to double click on graph. Make sure that the voltage is set on the y-axis and the current is set on the x-axis. Now the purpose of this graph is that we want to get the value of the resistance for part 1 at every length. Okay, so we are using the principle of Ohm's law that we did before. So we have the voltage plot on the y-axis and the current on the x-axis. We know that this relation should be linear and the slope of the line represents the resistance. So we will use this concept in order to find the resistance of each section of the conductor. This is the resistance and resistivity apparatus. Now, this apparatus consists of these pieces. One of them is fixed and the other one can be moved. So now, the purpose of this apparatus is to hold one of these wires. So we have 4 wires with 4 different diameters. If you sort them out in front of you, you will be able to tell which one is which. The diameters are listed in the lab manual. Now, for example, let's say that I want to insert this wire into the apparatus. Now, notice that each of these 2 connectors can be slided past the 0 for this one. This is the 0. So if you slide it past the 0, there is a piece here which will lift up this connector part. Okay. Once it is lifted up, you can insert the wire underneath. We'll do the same thing for the other side. So this is the 24 centimeter mark. So I'm going to push it past that. So now it is lifted, and then I can unscrew these 2 mounts and insert my wire underneath. Notice how it goes in very smoothly and easily without any resistance. If you feel any resistance, this means that something is wrong. Maybe you have to undo the screw even more a little bit. Then you simply screw these, just make them snug. Do not over tighten them because this will deform the wires. Okay, make sure that the wire is straight and nice. Now you can put this back to 0, and then you can set this to the length that you want. Okay, so in the lab manual, I think the first length is 4 centimeters. So now we have it at 4 centimeters, as you can see here. Take a look at the circuit diagram right here. So we have these 2 terminals connected to output 1 of the power, which is the power supply. This is the part that we can move from 0 to 24 centimeters. And the other one, the black one, is the one that is fixed at 0 centimeter. So these 2 are connected to analog channel A, which allows us to measure the voltage. So this is actually going to be the voltage sensor. So let's start with the bottom of this circuit diagram. So here are the 2 connectors that we want to connect to channel A, which is through the voltage sensor. So here is one, here is the other one. And these are referred to the horizontally mounted connections in the lab manual. These 2 are referred to as the vertically mounted connectors, which are, according to the diagram, connected to output 1 of the power supply of the interface, which is the power supply of this experiment. So here's the black, and I'm going to connect it with the negative side, and the red with the positive side. And as a check, if you read here, it says power. Okay, it says power right here. This is to remind you that this is connected to the power or power supply, and also another one here, it says power on the other side. Okay. So this is a reminder to make sure that you connect the power to these 2 terminals. Now you can change the length, and for each length you can, of course, after you set up the program, then you can find the resistance of each section of this wire by changing the length. So the resistance of this length can be found, and then the resistance of this length can be found, and so on, according to the lab manual. Now, after you're done with this part, then you want to start with part 2 of the experiment, in which we have to change the cross-section area of the wire. To do this, we'll have to keep the length constant at 24, and then repeat the experiment for 4 different wires. Okay. So to do this, I'm going to replace the wire with the next lower one in cross-section area. So again, to replace the wire, remember to move the two connectors past the stop and then undo the screws, and then the wire should slide out very smoothly. I'm going to replace it with the one with lower diameter or lower cross-section area. See how it is very small, and then just make it snug, do not over tighten. This goes to 0 and this goes to 24, and then you take a reading to find out the resistance. So in this part, in the second part, you'll find the resistance as a function of cross-section area. So you'll repeat the same thing for the two other wires that we have here. Now we have everything set correctly. So I'm going to start recording. And notice how my data is in this small portion of the screen. So I'm going to resize by clicking the auto scale. And here is my data. So according to Ohm's law, this should be a linear relation. And the slope of the line represents the resistance of this section of the wire. So again, in this example, I have a 4 centimeter section of the wire. So the slope of this line represents the resistance, which is 0.00493 ohms in this case, which is a very small value of the resistance. Next, I will change the length to 8 centimeters and repeat. Click record. And here is the slope of the new line. So you will repeat this until you finish the values in data table 1 of this experiment. So in part 1, we will end up having 6 lines, and we will plot all of these 6 lines on the same graph. So in order to do this, notice that in this example, I have only 2 lines. So in order to view all of my data together, I'm going to activate the multi-run by clicking on this triangle, and then click on the arrow here and select the runs that you want to display together. So in this case, I have only 2 runs, but in your case, you'll take a total of 6 runs. So we should see 6 lines together on this sheet. Okay. So after you're done with these 6 lines, make sure that you print this out and attach it to your report. Now for part 2 of the experiment, we will do the same thing, but without changing the length. We will keep the length constant at 24 centimeters, and we will start changing the conductors themselves. So we have a total of 4 conductors. So for part 2, we will see a graph that has 4 lines in it. Okay. Once you are done with part 2, make sure that you print out the graph. So again, to summarize, in part 1, we will have a graph with 6 lines and 6 slopes, which represents the resistance as a function of length. In part 2, we will have a total of 4 lines and 4 slopes, which represent the resistance as a function of cross-section area.